Hello everyone, I'm Jo Ashbourne, the Director of the St Cross Centre for the History and Philosophy of Physics, and I'd like to warmly welcome you all to today's special event in association with Oxford's Department of Physics. We have nearly 500 people joining us today from all around the world, so good morning, good afternoon, and good evening across the time zones. We're also delighted to welcome all the panelists, discussants, and our discussion panel moderator. Such an extraordinary group of space scientists will give us some fascinating insights today on the history and experience of space travel. Our moderator is Dr. Alice Bunn, International Director at the UK Space Agency and Vice Chair of the Council of the European Space Agency. Alice also co-chairs the World Economic Forum Future Global Council on Space Technology. But perhaps topping all that, one of Alice's most inspiring achievements yet might just be that she's introduced a space badge for girl guiding. So with that, I'll hand over to Alice, who will introduce our panelists and discussants. Thank you, Alice.
I'm absolutely honoured and humbled to be your moderator here today. I'm sure you're going to have a very, very exciting next 2 hours. We will be joined first by our speakers. We have Dr. Jim Green, the Chief Scientist at NASA, followed by Professor Mikhail Marov, the former Scientific Secretary of the Soviet Space Council, followed by Professor Günther Hasinger, the Director of Science at ESA, and finally Professor Yidong, the Chief Scientist of the China Manned Space Program. Now, as if that wasn't enough of a star-studded lineup, before we go into the full panel discussion, our speakers will be joined by 2 additional panelists, Dr. Mae Jemison, the former NASA astronaut and the first African-American woman in space, and Wing Commander Rakesh Sharma, the former cosmonaut and first Indian in space. I'm sure we will have a very, very lively discussion. Please do put your questions in the chat bar. Don't hold back. I'm sure you won't. And without further ado, I'd like to kick off today's event with a talk from Dr. Jim Green. Jim, over to you.
Well, thank you so very much, Alice. It's just a pleasure to be able to come and talk about what NASA's been up to. You know, it's very hard in the next 20 minutes to give you much in the way of details, but indeed there are a number of milestones in the space program of considerable importance that indeed I want to talk about. Let's start with NASA's fleet. This is what gets us into space. And as we see to the left, starting from Redstone all the way up to Saturn V and the shuttle, NASA's continued to develop more and more capable rockets. You know, the Redstone actually is the rocket we call Explorer 1. It's in that Explorer series that launched NASA's first scientific instrument. And those instruments were launched in a very rapid sequence. It was the tremendous opportunity for scientists in the 60s and well into the 70s to fly an instrument and learn something new just by turning it on and looking and making measurements. Just a spectacular time. And then, of course, from a human exploration point of view, moving from our first Mercury mission with a single astronaut, then to Gemini, and then, of course, the Apollo, as we see in the lower right, the Apollo capsule, and then on to the moon with the lunar LEM, the lunar landing module. And then, of course, we went through an era where we built things in space. We repaired things in space. This is the concept behind the space shuttle. Let me then start with some of the key elements of these programs. In the Apollo program, where we had 3 astronauts in a capsule, along with a lunar module, an ascent-descent stage. We've landed on the moon. These are the 6 locations on the moon where humans trekked out, put the first instruments on the moon. Several of them actually, like the lunar laser reflectors, are still operational because they are passive instruments. We can shine a laser to the moon, hit one of these laser lunar reflectors, receive the signal back, and of course we know the speed of light and we can determine the distance to the moon. These were unbelievable amount of information coming back in more than 850 pounds worth of lunar material, regolith, rocks. Fabulous set of material that we learn many things about the origin of the moon and therefore the origin and evolution of both the Earth-Moon system. Of course, now space station used by the shuttle to be able to assemble. The shuttle brought much of the material up is approximately the size of a football field. And it has a tremendous number of scientific experiments on board. So here's a little tour of the inside. Looks a little busy, you know. It's kind of a geeky in a way with the wires and everything all over the place. But indeed, the microgravity environment provides opportunities to do a variety of experiments, understanding combustion, understanding life science, and understanding how the environment of zero gravity or what we call microgravity, or still just a little gravity there, really affects humans in space. And it's our first major foray into many years worth of doing spectacular experiments. For the last 20 years, there has been humans in space, and they have been on space stations. So many in our audience, many of our young people have grown up in an era where there's been someone in space all the time. Just an unbelievable concept. Now, in addition to the human exploration part of our program, NASA has several specific disciplines where we have an array of missions. In the Earth science area, we have a significant number of missions that really look down and study the Earth. They study the evolution of the climate, looking at CO2 distribution, winds, aerosols, cloud patterns, land, ocean, and indeed atmosphere interactions. And these missions are the ones that are currently active or will be soon. They're all been approved to, if they're not in space, they'll all be approved and be launched over the next several years. These are the ones that are operational at the moment. Now, in addition to those, we've had many missions come and go in the past in these disciplines. Another set of missions are in the heliophysics area. This is an area of study that has the sun and the magnetospheric environment of the Earth, the space environment. This has really sensitized us to what we call space weather. Yes, there is weather in space. In other words, variations of not only electromagnetic spectrum, but more importantly, the particle measurements that are being made where we have coronal mass ejections and flares causing environmental changes that are important for us to understand because of the concepts of humans traveling in space. But they affect our magnetic field. Our magnetic field rearranges itself to adjust to these changes in space weather and causes aurora, which then creates ionospheric currents. Those currents, in fact, affect a lot of our ground-based systems, our power grids. And so indeed, we're studying the sun, how active the sun has been in the past, and how we could predict massive storms from the sun that could indeed affect our life here on Earth and our environment because of our technologies that we currently use. In addition to Earth science and heliophysics, we have a tremendous astronomy program. Of course, being able to go to space enables us to look with telescopes in wavelengths that we couldn't do from Earth because of our atmosphere's ability to absorb the really high energy X-rays, ultraviolet rays, and even elements of the infrared. and part of the radio spectrum. There's only a few areas we can from Earth really interrogate, but from space, all that opens up. And we have just a tremendous array of operating spacecraft currently that's going on. And in fact, we even utilize airplanes where we can get above a certain height in the atmosphere and allow us to study in the infrared. What we have then also is NASA supporting planetary science. You know, soon after the US space program studied and found radiation belts and made measurements in the Earth's magnetosphere, we then trekked away from the Earth. We then had more than 20 missions studying the moon before astronauts came to the moon, before the Apollo program. Those missions, of course, are no longer operating. Here is the fleet of planetary spacecraft that's currently operating. We have now plans for the moon coming up very soon, and also with Mars. Mars is one of the top objects, planets that we have studied. Here are the NASA missions. There's the array of NASA missions for which they have gone to Mars and flew by or orbited or landed or roved. And now with Perseverance, we're in the process of being able to create samples, and then we'll return those samples to really give us the understanding of how Mars evolved. We know Mars, for instance, was a blue planet very early on in its history, 3.5 to 4 billion years ago. It was more Earth-like. It had a very extensive atmosphere. So it had clouds and it had rain. 2/3 of the northern hemisphere was underwater. And this was a fabulous time in the history of this planet, but something happened. Rapid climate change occurred, and Mars is now the arid planet we see. When we're on the surface and we rove, we see a lot of what we would think is familiar, in the sense that many areas in the Southwest, in particular in the United States and also Australia, other locations on this globe, have this arid look and feel about it. And so Mars in many ways is strangely familiar. So really exciting set of missions that are going on. Soon we'll drop off the belly pan of Perseverance, a helicopter, and we will then begin the process of figuring out if we can actually fly these kind of missions on another planet in an atmosphere, which will open up vaster regions for us to explore on Mars in a quicker time frame. Well, let's turn our attention in the last few minutes that I have about some of the future activities in science and exploration. Of course, we're working hard with our partners. ESA is one of our top partners that have been involved in James Webb Space Telescope. This is an unbelievable telescope. It's a 6.5 meter diameter, which is 21 feet in diameter. It's the largest telescope ever launched. We're moving towards a launch in the October timeframe of this year. It also looks at a mostly infrared, a little bit of the long wavelength visible area, but it's going to open up, we believe, in greater capability this particular set of wavelengths, and then tells us much about what's happening not only in our solar systems that radiate, absorb heat from the sun, and then radiate in the infrared. Those will become bright, but also looking back in time, can look at wavelengths which tell us what may have happened in the early formation of galaxies. And so we're really anticipating this. NASA now is also building a brand new rocket, more capable than not only the space shuttle, but more capable than the Saturn V. And this is called the Space Launch System, SLS. We're developing also a major capsule. This is the Orion capsule. This will be able to get us to the moon. And in fact, the current plan is laid out in this particular chart for the next several years. Our plan is to perhaps later this year, late this year, November, December timeframe, we're still on schedule to launch Artemis 1. Artemis 1 will use the Space Launch System with the Orion capsule, the first uncrewed use of that system, where we'll take a figure 8 around the moon and come back. And then we will, with Artemis 2, soon after, once we learn how that system is working in space, launch our first set of astronauts to do pretty much the same rendezvous. In the meantime, we're continuing to build a whole variety of systems, not only those that land on the surface and make measurements, but a smaller space station we call the Gateway. This is where we're going to come and then dock. We will also have a descent and ascent stage going to the moon and returning. And this would be for Artemis 3. So this is just a tremendous set of things that we're working on now, which will be able to put the first woman and the next man, or perhaps the next woman also, that hasn't been decided, on the surface of the moon. And the area we've selected is the south pole of the moon. This is a tremendously fascinating area that may have trapped in its crater some beautiful volatiles and water and resources we can use. These are finally the set of NASA and commercial partner missions that we plan to use just in the next several years. So we're really looking for an exciting set of new activity on the moon as we learn to live and work on a planetary surface, with the end goal being Mars. So thank you so very much, and let me turn it back over to Alice.
Thank you, Jim. That was absolutely fascinating, and unsurprisingly, I can already see a huge number of questions appearing in the chat bar. We will come to those later in the panel discussion, although I'd also invite our speakers to contribute to those questions live as we go along. In the interest of time, I wonder if we might just then reverse the order, and perhaps I could invite Professor Günther to give your presentation now.
Thank you very much. Thank you very much, Alice. Yes, very good. So I'm also happy to talk about the history and future of space travel viewed from ESA. And I'm the director of science of the ESA program. So I'm not responsible for manned space or a crewed space flight, but I'm also able to show you a little bit about the excitement of our astronauts in space. The cupola of the space station, which is also sometimes inhabited by our European astronauts, and the person who is currently preparing for launch is Matthias Maurer, who will do the next mission, Cosmic Kiss. And then also Samantha Cristoforetti is getting ready to be being prepared for launch. And we are very excited to have kicked off a new astronaut recruitment campaign. We are inviting everybody interested to apply. And in principle, this next generation of astronauts will also have a chance to work together with NASA on this exciting possibility to go to the Gateway and even forward to the moon. So we are really living in a very exciting times for the astronauts. Now, we have all been extremely excited and also impressed about the NASA, the technical skills of NASA, that they have just demonstrated landing on Mars again with Perseverance. And I want to show you a little bit about the somewhat more checkered history of landings that the European Space Agency was able to do and throughout the history. What you see here is actually the Solar System Fleet. And you see on the bottom the history. We are standing on the shoulders of giants in a sense. You see here the current missions that are ongoing in the particular solar system, and then you see the missions that we are preparing. Many of them are done in cooperation with our partners, with NASA, with JAXA, with Roscosmos, and also with the Chinese Academy of Sciences. Now we have 4 landings that we are really proud of. that I would like to quickly talk about. We have landed something with Mars Express. Cassini-Huygens, together with our partners, was the most distant landing so far done. Rosetta is in everybody's mind, the hopping on the comet, and then also we are working towards the Exomars rover. And just to give you a bit of history, you know, in 2003, we launched Mars Express, and there was a little object called Beagle 2 on it. And unfortunately, Beagle 2 was regarded to be a complete loss. But recently, Beagle 2 was actually recovered and found back. When you are looking with this is the Mars Reconnaissance high resolution camera. And when you look in detail, then you actually see an object on the surface of Mars, which is basically Beagle 2, but it is not fully unfolded, unfortunately. It's only half unfolded, and therefore we now know that it landed successfully, but it didn't work because the antenna was not switched over. This was our first experience of landing something on a planet. The next experience was done together with NASA, and beautiful work together in the Cassini-Huygens Saturn system. And we were indeed landing on a planet, on a moon of a planet, Titan. And this is the picture of the surface. Now, when you compare the animation of the landing sequence, and then you compare that to the excitement that we got in real time and live from Perseverance, this is clearly a generation further in the past, but it is still the most distant landing that has ever happened in the solar system. Then the excitement grew with the Rosetta instrument that flew around the comet 67P Churyumov-Gerasimenko, and that was also putting down the little hopper Philae. And this is actually the sequence of Philae landing on the surface of the comet. Now, unfortunately, the surface didn't turn out to be the one that we expected. And so Philae didn't really land, but was hopping around on the surface of the comet, and then finally ended up in a little corner on a place of the comet, namely here in cracked away in the shadow. But still, Philae was a great success in this respect, because it gave unprecedented information about this comet together with Rosetta. Then there was another unfortunate situation, that was the Schiaparelli lander on ExoMars 2016, which this was unfortunately really unsuccessful, because there was a software failure which interpreted the mission to be already landed while it was still 3 kilometers in the air. And so we have created a new crater on Mars, the Schiaparelli crater that you can see here. Nevertheless, I mean, space is difficult, and but the excitement is nevertheless mounting and getting bigger. This is the beautiful place where now Perseverance landed in the Jezero crater, and this is a picture from Mars Express in all its beauty. And when you look in detail, then you see the landings of Perseverance. And I'm very happy, as Jim already said, we are working together with NASA. A lot of the data that you see coming down are also transmitted through our assets around Mars, through TGO and partly also through other assets. And this picture actually has been transmitted through the trace gas orbiter, so we are really proud to be part of the history that NASA is writing there. Then let's move on. This is now a little bit the current and future. We have launched a mission that is going to Mercury. Mercury is the innermost planet, and it is a very, very difficult to understand planet. It is much heavier than it should be. This is a beautiful picture from taken by the NASA mission to Mercury, and we are on our way there. And while Bepi Colombo is flying there, it is also coming by Earth and Venus. And this is actually a nice sequence where 2 flybys are showing the sun coming by Earth, and then also Venus lately. Then just about a year ago, a little bit more than a year ago, we launched Solar Orbiter, which is a mission that is flying close to the sun. Not as close as Parker Probe, but it is the advantage of Solar Orbiter is that it will also elevate its orbit and it will actually be able to look at the poles of the sun. And Solar Orbiter has already provided us with huge excitement in the very first data that came up last year in summer. We have discovered something completely unexpected, so-called campfires on the sun. Very, very hot pieces of the sun that may well be responsible for the X-ray corona. And this is something that has been completely unexpected, and it promises a great future for our Solar Orbiter spacecraft. And since this is about space travel, this is another perspective where Solar Orbiter is actually looking back at us. So Solar Orbiter is close to Venus here, and then this is Earth, and this is Mars. And when you look in detail, then this is Uranus. So Solar Orbiter is actually then traveling through the solar system, and we can really follow it and watch it. Together with also the NASA missions, but also the ESA assets, Cluster, Bepi-Colombo, Solar Orbiter, Swarm, which is an Earth observation system close to Earth. We are also part of this huge effort to understand space weather and to try to understand how the plasma is affecting us on Earth, but also affecting astronauts on Mars and Moon. And then something very exciting is coming up next year, where we will launch a big spacecraft to the icy moons of Jupiter, to these exciting places like Europa, Enceladus, and so on. And the JUICE spacecraft is just being readied for launch, so it's almost there. I just want to give you a short picture. So that brings me to the Astrophysics Fleet, because similar to NASA, we are also looking up, not only down and inside the solar system. And again, here we have a large number of missions, which are our legacy missions, very famous ones. And currently we have a number of working horses, and one of these working horses is the Hubble Space Telescope. But Gaia, I would like to also point out, is a very exciting mission that is really producing huge amount of new knowledge. And Cheops is a little exoplanet mission that has also excited us with new beautiful results. So let me start with Cheops. Cheops is a small spacecraft which is looking at known planets, but it can actually learn more about these planets, exoplanets around other stars. And this particular case is actually a planetary system which quite surprisingly had 6 planets that are in a harmonic orbit rotating around the star, which is almost like our sun. And when you are putting these orbits around, then you can actually see that they are in harmonious synchrony. That means, I don't know whether you can hear the sound, but whenever there's a little blip, then you see that 2 or 3 or sometimes even 4 planets are in this hierarchy and harmony. And this is something very rare, and Cheops has found one of these cases. Now, just towards the end of the talk, let me come to our working horse, Gaia, which is really a very powerful instrument that gives us a new picture of the universe by looking at the billions of stars and by very, very accurately measuring these billions of stars, how they move on the sky. And from their motion on the sky, we can determine their distances. We can also determine their real, true velocities in space. And the most recent picture of Gaia came out in December, just a few months ago, where we now have very, very accurate determinations of stars moving in the Milky Way. And one of the most exciting results from Gaia was that actually a fraction of the stars in our Milky Way behave very non-like the rest of the stars. Most of the stars move around the Milky Way in orbits around the galactic center. But there is a small fraction of stars that are actually seem to cross the Milky Way and crash more or less through it. And this is the result of a merger of another galaxy with our own Milky Way. When you look this little simulation and you see the Milky Way originally is, let me see, does it go? And you see that the Milky Way originally is actually thin. Unfortunately, this doesn't run. Oh, it runs, okay. And then after a while, this little red galaxy is coming through, and it's crashing through the Milky Way, and it's reorienting the stars and makes the Milky Way into a kind of thick, more donut shape like structure. And so we can, with Gaia, still basically unravel the history of the Milky Way and can also say how it was being built up together. And a very recent result that I would like to close my presentation with is that with Gaia and with Planck, we are actually able to measure the absolute motion of our sun vis-a-vis the rest of the universe. Planck is measuring the absolute speed, which is about 670 kilometers, and is then showing up as a dipole of the background radiation. But very recently, Gaia has actually been able to measure our acceleration of the sun in its orbit around the Milky Way. So the sun is not moving in a straight line. It is continuously accelerated and falling towards the center of the Milky Way. And this is actually visible as something like when you're driving through a snowstorm, then it looks like all the snowflakes are coming directly towards you. And so we are actually able to measure an acceleration or a speed of something like 0.1 nanometers per second, which the sun is actually moving around. So this is a really unprecedented precision, which is only possible by something like Gaia. And with this, I would like to end and say, okay, we are working to create more new knowledge. Gaia is one of the very, very big knowledge creators in the last years. It has outshined almost all other astronomy missions in history. And we are preparing now together, and I don't want to dwell on that, together with NASA. Actually, NASA is preparing James Webb. We're very proud to be partners on that mission. On our own side, we are also very excited for the next large missions where NASA is a partner and JAXA is also a partner, where we want to look at the emerging black holes, both with X-rays, with Athena, a large X-ray telescope in the future, and with LISA, a gravitational wave telescope. And that is what we call bringing sound to the cosmic movies. We would like to see basically movies with light and sound. And this will actually be one of the big projects in the future. There are great new ideas coming up. So we already discussed Voyage 2050, which is giving us priorities for the next 25 years. And so there's really a bright future for space and space exploration. Thank you very much.
Günther, thank you very, very much indeed. I think we are preparing for a absolutely fantastic discussion at the end of this. I can see the makings of that discussion already appearing in the chat bar, with already a debate of the relative merits and disadvantages of human versus robotic exploration, for instance. But we shall come to that later. I would like to turn to Professor Marov, if Professor Marov is ready.
Good afternoon to everyone. First of all, let me appreciate an invitation to participate in this panel discussion. And I will try to tell the main stories about the Soviet and some part about the new Russia space program. And it will be a sort of overview. I apologize for possibly a very brief discussion of the main issues of these historical processes and very important milestones in our space program. Historically, it was very important steps in space exploration undertaken by former Soviet Union. And first of all, certainly at the launch of the first satellite in 1957. Also, it's extremely important first manned mission with Gagarin flight, and very important results were also obtained about our space environment. And while this mission had been mostly motivated by the Cold War imperatives, they very much advanced our knowledge and space science and technology and paved the road to the future space endeavors. We were very much lucky to have extremely important leaders in our space program. It was very people of the absolutely great intellectual capacity, Sergei Korolev and Mstislav Kelzysh. They played the extremely important role in the advancing and basically even in the creating of our space program. And the program and projects were driven by specially created Space Council with Mstislav Keldysh in charge. It was not governmental body, but it reported to the government, and the main decision of this council were endorsed by the government. And I had the privilege and great opportunity to serve like a scientific secretary of this council for nearly 20 years. Let me just recall you about the historical Gagarin flight. We will celebrate soon in next April, the 60th anniversary of this flight. This is shown, this historical launch, and this is the Vostok spaceship, which with Gagarin inside the flight for only one time orbiting the Earth, but it was extremely historical flight. This is the picture showing the Gagarin and shaking hands with Korolev, Keldysh beside, and the many peoples of the special commission, governmental commission responsible for this flight. This is Gagarin after returning back to Earth, and this is the Vostok space capsule. I like this photo because it's Gagarin. He is just an ordinary person, not like an icon, which we used to have in different kind of images. Several words about our flights to the moon. That's the first flights outside the planet Earth. And also I will concern a little bit about Lunar Race. Well, this is the first generation of the lunar missions. That's the first impact to the moon. This is the first images of the lunar far side. This is the first soft landing on the moon surface and returning back to Earth, the first lunar panorama. This is the first satellites of the moon. And this is an absolutely fantastic picture. I just remember myself, I just look at that with the open mouth of mine, because at the first time we could see the moon with so great resolution, about 1 millimeter. And it was also broad evidence that it's quite rigid, at least enough in order not to dive inside like it was initially suspected. Well, this is some diagram we're showing with our involvement in the lunar race. Well, it was historical process when USA decided to chase Russia, Soviet Union, in order to compensate some kind of the losing prestige after Gagarin flight. And it was several important components of this mission. First of all, it was just the development of the heavy rocket N1. Then it was several orbital modules which was launched, and also it was some precursors of landers and orbital stations, which was quite successfully implemented. Well, it was also several flights with a lower capacity rocket, Proton, which was tested special spacecraft Zond. It was several successful flights, and they returned back to the Earth with the second space velocity. This is the showing this Zond at the top of this Proton rocket. And this is the first so-called LOK, the spaceship in order to orbit the moon. Well, it was several times successfully tested, but it's like it's the remnants of this development at that time. It was the new transport spaceship Soyuz, which widely used until now for the orbital flights. This was several testing of lander on the moon, with the one cosmonaut intended to step on the moon, and it was also successfully tested in the Earth's orbit. But we were unsuccessful to implement the program and to be successful in this process, because its heavy N1 rocket turned out not quite well designed, and several four tests, all well failed. So it's basically prevented us to step with the first man on the moon. It was even prepared the crew of cosmonauts for the flying in the moon orbit and to step down on the Earth surface. Alexei Leonov was first man nominated for this historical mission. Well, but instead, in order just to compensate somehow our damage, which was followed from our losing the moon race, it was very clever ideas which was put forward by the very intellectual people, George Babakin, chief designer, who suggested, and he was supported by with the idea to undertake several robotic missions to the moon. And it was quite capable robotic mission with the sample return and the lunar rovers. This is the image of the first Luna 16 for the sample return. This is a slave arm, and this is the special manipulator in order just to put soil from the surface to the return capsule. And this is return capsule on the Earth's surface. And this is the lunar rover, which operated on the moon surface for 11 months. And this is the second one, which is a little bit more capable, very better instrumented, but it operated a little bit later because of some kind of disadvantage which was made by the operators. This is the traces on the lunar surface left behind by the lunar rover. And also, Babakin was responsible for our progressive missions for the planets in planetary investigations. This is the first of all very successful Venus program with the generations of the Venera stations. First generation allowed us basically to reveal the main parameters of the Venus atmosphere, and later on the surface, the properties of the surface. This is the capsule with lander, which successfully just landed on the Venus surface. And this is the second generation of this spacecraft, which allowed us to investigate in detail the atmospheric properties, heat budget, microphysics of the clouds and composition, and so on. And this is even the most advanced spacecraft landers, which allowed us to take samples and to study their composition and also return back to the Earth color panoramas. And this is, in fact, just at the close-up view of the Venus surface. Also, we pioneered the process of radar mapping of Venus surface with quite capable instruments, this radar antenna, and it was mapped by the northern hemisphere, and the full mapping was made by the USA Magellan. Well, it was also the basic project, I mean, Venera spacecraft generation, which allowed us, based on this design, to flow for rendezvous with the comet Halley. And this is the bus which made such flyby, and in order just to take image of the comet Halley. Well, we were less successful with the Martian program, but nonetheless, we made the first soft landing on the Mars. Unfortunately, the signal from the surface was very suddenly terminated, and it was just mostly technological success. But in 2 years later, we were quite successful to measure first first direct measurements of the Mars atmosphere. And this is the lander, how it was just designed for these projects. Well, it was followed by our flight to satellite of Mars, Phobos, and it was quite only partially successful, but it was by photometry with the first measurements of the Phobos surface composition. Well, in the middle of 90s, it was undertaken very ambitious mission, Mars 96, but it was already during the time after so-called perestroika, which was dramatically impacted on our social, cultural life, and very badly impacted on the industry, including space facilities. I've been nearby this testing spacecraft, and I remember that the people who worked for the preparation for launch were basically partially hungry. And it was very unfortunate time for us, and certainly it was hardly possible to expect that the mission will be successful. And indeed it failed. And it was very badly impacted on the whole planetary program. We started to recover quite slowly, only in the first decade of this century. And it was with the next Phobos mission, with the main goal of the Phobos sample return. This is a spacecraft, but also, unfortunately, this mission was failed. Well, all the historical missions, specifically robotic mission developed in former Soviet Union, quite in detail described in this book published by Springer, Praxis, and this is with my name, I co-worked to Wesley Huntress, former assistant to NASA administrator. We were very friendly and still very friendly for years. And this is important heritage describing this historical process of our robotic mission design and important discoveries. And by the idea, a suggestion of Wesley Hundreds, it was said, first on the back cover of this book, first on the moon, first on Venus, first on Mars. And the book was awarded by the Special Diploma of International Academy of Science. Well, very briefly, just to mention about our astronomical missions, that the most important in the former Soviet Union, it was Granat, Astron, Quant. Now it was already in this second decade of the century, it was Radio Astron, and right now operating Spectre and Gamma. Very ambitious mission right now ongoing. It's a Millimetron mission. And this Radio Astron was at the first time accomplished a resolution for the absurd galactic objects up something like 1 millionth of arc second. This is very important and quite well maintained, even in the destroying years after Perestroika. It's a manned mission. This is the Soyuz Apollo docking. This is the Salyut orbital station. It also quite first full-scale orbital station. And it was baseline for the development of the Mir orbital station. This is the docking with the shuttle in the 90s, and it's just eventually very good experience gained during these missions, and their operation design was implemented for the our segments for the Mir station. Well, saying about the future, I would say, first of all, quoting famous American author Mark Twain, rumors on my death are too exaggerated. Well, the same I could address saying about our Soviet, right now, Russian space program. National program is mostly focused on the moon. And we have quite ambitious program of these missions, including just deployment of the lunar base. There are also projects for the Mars study, and Exomars is already operational. I mean, the first part of this mission, second, is going to be launched in 2022. Well, we placed instrument on some NASA mission and ESA mission as well. Well, we are going in our blueprint program to return back to Venus, to Phobos sample return, and to Mars mission, and certainly with several quite ambitious astronomical space observatories. Well, we quite well advanced in the human missions, and this just right now addresses us as a pathway for flying to Mars and beyond. This is our lunar program. This is the first mission, Luna 25, which is scheduled for October this year. Then it's the orbiter. This is the quite well instrumented mission for study lunar surface nearby South Pole, and with to be followed by the quite interesting and well instrumented mission for the cryogenic sample return. And also it should be quite capable lunar rover of the next generation, much more advanced compared to already launched. This is the concept, Roscosmos concept of the lunar base configuration, and just what we are going to implement since the beginning of 30s of this century. So, just to conclude, we just started important space exploration program, is launching the first satellite in 1957 and achieved great successes during the first decades. And this is some kind of this success listed in these slides. I would specifically just highlighted such flights like first man, first woman, first spacewalk, and also there are several important missions to the Moon, Venus, Mars, and certainly there are first orbital stations and first robotic lunar sample returns and Lunar Rover. Well, unfortunately, stagnation in space exploration, lunar planetary science, and space astronomy caused dramatic social economic process in the country, very badly impacted on our, I would say, more or less traditional, interesting and important space missions. But resurrection of space science program right now ongoing in the new Russia. Thank you.
Thank you very much indeed, Professor Marov. What an absolutely wonderful historical guided tour, I would describe that, through the former Soviet Union's and Russia's space achievements. I think it's always very, very striking, particularly when you look back to that time 50 or 60 years ago when those developments were happening quite separately, but actually there's so much similarity across the capabilities that were eventually produced. And I think equally striking is when you look at the more recent efforts in space exploration and space science, where you see to a large extent a greater degree of international collaboration. And I can see some of those themes around international collaboration coming through in the questions to the session. So maybe we shall pick up on that later. But without further ado, I'm delighted to introduce Professor Yidong Gu. Over to you.
I'm happy to join the discussion panel. I come from the Chinese Academy of Sciences, and the chief scientist China's manned space program. Also, I joined some astronomy satellite mission. Overall, during past 30 years, China has made remarkable progress in space science and technology. China has carried out the manned space program, Moon and Mars exploration mission, and promoted the capability of space transportation launch facility, TDLC network. Now, China becomes an active participant in space travel and the exploration of the world. My talk consists of 3 sections, including our views of China's human space mission, lunar and the deep space exploration, and the future plan. In 1992, China has decided to implement the manned space program. This slide shows the developing strategy. We start with the developing spaceship, send the astronaut into space and return safely. Then, development of space laboratory to test radar docking and the EVA procedures. Above 2 stages has been successfully completed. Now we are going to build a space station, conduct a series of scientific studies, and prepare for future moon and deep space travel. The Shenzhou is a Chinese manned spaceship. Since 1999, there was 4 unmanned demonstration flights. The first manned space flight was conducted with the Shenzhou 5 on October 2003. Then the Shenzhou 6 and the Shenzhou 7 flights were followed by 2 persons and 3 days missions, and 3 persons for extra vehicle activities. Now let's see the China Space Laboratory Tiangong 1. Tiangong means the Heaven Palace in Chinese. Tiangong 1 was launched in 2012 and operated for 4 years. 3 spaceships were visited, and the 2 groups of the astronauts were worked in for 12 days and 15 days, respectively. Tiangong 2 Space Laboratory launched in 2016 and in orbit for 3 years. 2 astronauts worked in Tiangong 2 for 30 days. A cargo ship Tiangong 1 delivered supplies and refueled to Tiangong 2. The Tianzhou cargo ship will be used for China's space station with a transport capacity of 6 tons. China's space station, which is a long-term mission, will start construction in this year and will be completed after 2 years. It consists of 3 main modules, including 1 core module and 2 experimental modules. The weight of every module is 23 tons. This slide shows the research facility in the experimental modules. You can see the rigs, and outside we have an exposed platform. This is a sky survey telescope flying accompanied with the station assembly. The main mirror is 2 meters, and the field of view 1.5 degree, and angular resolution is 0.15 seconds. It could be docked with the station's assembly for maintenance and installation of the new terminal instrument. The next section is China's Moon and Mars exploration. Chang'e, you see, the China's lunar exploration project names the Chang'e project. Chang'e is a Chinese moon goddess in traditional story. We start with the lunar orbiter observation. Both Chang'e 1 and Chang'e 2 are lunar orbiter. They obtained 3-dimensional image with the resolution of 7 meters and detected the material components in moon surface and the underground structure, something like the several 10 meters. Chang'e 3 and Chang'e 4 is a landing and patrol mission. Chang'e 3 made a soft landing on the Red Sea area in 2013 and take the rover patrol. Chang'e 4 landed on the Von Karman impact crater in Mumbai in 2018 and carried the patrol. The rover is still working now. Chang'e 5, the sampling and recovery mission is carried out during December last year. Have obtained 1.7 kilogram samples through drilling and surface sampling, then return to Earth safely. This is humanity after 44 years from now, once again completing lunar sampling campaign. The Chang'e project will continue and has planned Chang'e 6, 7, and 8 mission, including study on the topography, water and at the moon's south pole, and test the technology for lunar resources insert utilization. The first Mars mission in China, named the Tianwen-1 probe, was launched on last July, which entered in Mars orbit since just about 2 weeks ago, then transferred to the parking orbit to conduct the orbit observation. It is going to land on the Mars in May, and a rover will investigate the Mars atmosphere, environment, and the evidence of the past or present life, something like a microbe. This is some photo of the Tianwen-1 mission. This slide shows the summary of the payload on orbiter and the rover of the Tianwen-1 mission. And next is the future space travel plan. In deep space exploration, we are considering the asteroid and the comet sampling return mission, Mars sampling return mission, Jupiter orbiting and other planetary survey, and the boundary of the solar system sounding mission. This mission partially in Phase A, the concept study, and some in the Phase A, we have conducted the preliminary design. Concerning China's human lunar program, since 2011, we have conducted a series of the argument and the demonstration. Now we are conducting a carefully demonstration and preparing. The final decision is underway. The photo shows our new spaceship, which can carry 6 astronauts. The module will be used for the moon mission. The red one is a new rocket model. The progress of China's manned space and unmanned lunar mission has made foundation to carry out the human lunar mission. We hope, firstly, to realize the Chinese landing on the moon. Then improve the ability of the Earth's moon round trip, moon surface residence, and man and robotics joint exploration. Then we hope to construct a lunar research station. We hope it expects to be an international station to serve for the continuous science research and ensure resources utilization. Finally, some personal view listed here for sharing. Concerning the future space travel, I think most important is to put attention to the joint exploration of man and intelligent robotics. And we need to enhance the international cooperation. Chinese scientists warmly hope for the close international cooperation. That's all. Thank you.
Professor Yidong, thank you so very much. It must certainly be a very, very exciting time to be working in space in China at the moment. There is a series of very, very impressive missions underway, and we certainly look forward to hearing more about those in the future. So I am valiantly trying to track the questions coming in the chat bar. And I can see that they're starting to group in a number of areas. So I'm really looking forward to our panel discussion. But before we go into that, I would like to have the pleasure of formally introducing Dr. Mae Jemison to join our panel, and also Wing Commander Rakesh Sharma. So perhaps I can turn to you first, perhaps to you, Dr. Jemison, for your reflections on what you've just heard, and perhaps in particular from your perspective as an astronaut. We're seeing quite a lively debate, I think, playing out on the pros and cons of human versus robotic exploration. So I'd be very interested for your thoughts in particular on that, and also any wider reflections from what we've heard so far. Over to you.
Well, thank you very much. I should tell you that it's been very exciting being here. And the excitement for me is the fact that we have representatives from the major spacefaring nations talking about not only the past, but the present and some of the future plans. And what I'd like to start off with saying is that as the discussion about space exploration started, we started somewhere around 1957 or so, but I'd like to push us back to understand that we are building on something that has been a human endeavor since humans have been here, because we're building on the fact that thousands of generations ago, across the world, across every society, people track the movement of the stars, of these lights in the heavens, and their ability around the world to predict what was going to happen, where there are going to be solar eclipses. People use them for guiding when to plant, recognizing the seasons, recognizing the tides, navigating. We are building up on that. The reason I bring this up is because I believe space exploration is very much a human endeavor. And it is not only associated with the physicality of being there, but it is part of who we are. In fact, an Ashanti proverb, an African proverb says, "No one shows a child the sky." It is very much a part of us. And I want to bring that into the context of my discussion and my interpretation of what I've heard. I should also tell people a little bit more about me. So I was a NASA astronaut. I flew on the Japanese Space Agency on a mission with Japan. It's called Space Lab J in 1992 on the Endeavour and the shuttle. And my background is engineering. I'm also a physician. And I lead a project called 100-Year Starship, which was a project that was started with seed funding from DARPA to ensure that we have the capabilities for human interstellar flight within the next 100 years. And that's capabilities, not launching a mission. And so our project, our proposal that won this modest seed funding was called An Inclusive, Audacious Journey Transforms Life Here on Earth and Beyond. And that's what I want to get to in terms of helping to supplement what I've heard here today. The inclusiveness, inclusion across ethnicity, gender, and geography, and inclusion across disciplines, because as we make these inclusions, we can do remarkable things. I think, as Professor Gu actually mentioned, that it is the joint combination of robotics and human exploration that makes a difference, that has these tremendous impact of what we've done, what happens here on the world today, and how our world has actually been transformed by space exploration. So it's really exciting as we hear about the different kinds of projects and actually the physicality of looking out beyond the Earth, understanding new planets, landing on the moon, being in space. But I think we would be remiss if we didn't talk about the impact that that has had on our planet and on our lives here every day from global positioning satellite systems, which we use for direction, remote sensing that we use for understanding mapping and where minerals are, and land management and agriculture, to the vast number of materials that were developed, to just even understanding monitoring the human body. So it's really important that we understand that space exploration has an impact not only for our thirst for knowledge, but also on what happens here on Earth. We saw that with every program. I want to add on, and so, you know, why humans, why crewed versus robotics? And everybody, I was always struck by the fact that everybody wants to bring this up as an issue. And I was able to read some of the questions and some of the assumptions. And I won't go into too much detail because I want to just give a summary first. But the reason why you have humans and the reason why you need robotics both are because they fulfill different needs and have different capacities. Robotic missions, probes, we're able to send with less certain safety procedures in place, right? Because if we lose the mission, you're not having the loss of life. So, and you can go into more dangerous environments. You don't also have to have the kind of life support systems and things that are required for it. And so there have been some remarkable things that have happened overall for robotic missions. We can talk about Viking all the way and some of the Venus probes that we heard about from Dr. Marov. We can continue and talk about those. And to Perseverance now landing on Mars, and Taiwan that's going to have a rover, as well as robotics when we do the observation even of HOPE that came from the UAE and that's now orbiting Mars. All of those are robotic and they have very special purposes. But when you look at humans, you talk also about flexibility. One of the issues of robotic missions now is that you have to have decided exactly what you're going to do, and you have less capability for modifying it or flexibility once you get in orbit or once you get to your destination. I would dare say that what we've seen from the Hubble Space Telescope being repaired on orbit to the types of experiments that can be done on space station. My mission was a mission where we was a laboratory mission where we took up frogs and we looked at embryogenesis. We had them ovulate and fertilize eggs. We started to understand a lot about embryogenesis. There were so many experiments that really required a certain level of manipulation, and we could do more. And I would dare say that that's going to continue for the foreseeable future. In the chat, I believe someone, or in the Q&A, someone said, you know, we have this incredible robotic and AI technology. It is still not the equivalent of humans. And the other part about having humans involved is what we learn as we try to create systems that support life in these very hostile environments. Those actually make an extreme, have impacted our world here today. Just the whole monitoring that had to go on from a distance, the telemedicine that had to go on from a distance during the Apollo program, affected monitoring of patients here on the ground. And I could go on and on with that, but I don't think it's an either or. It is one that is done in combination. And the other piece that I'd like to pick up on this as that I saw in the chat, the other couple pieces I want to pick up on is the commercial exploration. Someone I think also talked about, well, why don't we just let humans be done with commercial, or why are governments still doing this when commercial exploration can do a much better job? I want to remind people that the reason some of the new commercial ventures can do such a remarkable job is because they're building up on the work that governmental organizations did before. So there is a tremendous amount of work that was done just getting to low Earth orbit back in the 1960s that could not have been sustained by a commercial entity. And so government has a role. This has a role in pushing us further than we know what to do. So there is a difference. That purpose, that usefulness is something that everybody gets an opportunity to see. If it was all left in the commercial industry, then it may not be shared the same way that we see the data and the information is shared.
Dr. Jemison, thank you. Thank you so much. I'm very conscious of the need to also introduce Wing Commander Rakesh Sharma. I knew I shouldn't have started with the most fascinating and the most controversial topic around the debate around human versus or human and robotic exploration. But it's really, really fascinating to hear your views. And I hope we come back. We're going to cycle back through those questions in the chat bar and have a broader panel discussion. So thank you. Could I turn now to Wing Commander Rakesh Sharma? I'd be very, very interested to hear your reflections on what you've heard from the panel so far before we open up to that wider panel discussion. Thank you.
Thank you, Alice. Well, first off, I must say that Dr. Mae Jemison has said it all, and I echo large parts of what she has acquainted us with her views. I must also admit that it was like going back to school, listening to our learned panelists from various countries, giving us an overview of history and what all has already been achieved and what is planned for the future. And I'd say that the last 60 years have truly been remarkable if we look at only the advances that we have made in the realm of space. During this period, apart from demonstrating that humans can survive in the challenging environment of near-Earth orbit, we've had moon landings. I'd say the moon landings were perhaps before their time at that time, and I'm referring to the human part of the landings. NASA demonstrated that really technology was available for humans to reach there and return safely. But the technology the staying power, the technology required to explore or much less exploit the moon had not yet matured. And of course, there were funding constraints too at that time. But today, when humanity is getting ready to return to the moon, and this time, not really to just return, but to establish a permanent human presence there. And I'm sure that after a brief period of exploration, we shall begin to exploit the resources which are available there, and we know what all is available. And I'm sure that my colleague Mae will share my concern and indeed that of all of us who have experienced space travel and have had the good fortune of looking back at planet Earth and the fragility of the environment of our planet. So today, it makes us wonder, and I'm talking about the collective of the Association of Space Explorers, it makes us wonder that going forward, how will we ensure that future exploitation of space-based resources will be carried out in a sustainable way? The questions that arise is, do we have a robust enforceable space law? Do we have an effective governance model in space? You see, now with the private sector playing a larger and larger role from here on, how do we ensure sustainable exploration with minimal damage to the existing environment at the destinations we shall be traveling to, first to explore and then to exploit? So our track record on our home planet really has left much to be desired in terms of these issues. And since our panelists are really heading and occupying very important posts in their individual countries' space programs, and they must obviously have a good insight into the philosophies that are being considered, that are being thought about, and the policies that are likely to flow from those thoughts. I would really look forward to hearing their opinions on this aspect, which bothers us, because we have really not grown in a sustainable way on the only planet we will ever probably inhabit. Of course, we will be going to the moon, but how do we make sure that we do not repeat the mistakes that we as a species have done on our home planet? So these are my concerns, and I would like to really go back to the panel and find out whether these aspects have been thought about. Of course, it's all very, and I'd like to pick up from Dr. Mae's talk that cooperation would be very necessary in future. But I've heard only Professor Yidong refer to this, where he has openly welcomed international cooperation. So really, what all do we need to do? How do we make this whole human endeavor a lot more inclusive? One aspect, of course, if I think back of my own space flight, when I was in orbit, I was part of a 3-man crew which had gone and docked with the Salyut, and there were already 3 other Soviet cosmonauts on board the Salyut. So we were 6. And while we were in orbit, the shuttle got airborne. So we were 11 human beings orbiting planet Earth. So there you have it, multinational, although not in the same craft, but a multinational crew orbiting planet Earth. And during my adaptation period, I had developed a problem with my spine. There was a strain which I had felt. And Dr. Oleg Atkov, who was the doctor on board carrying out his medical experiments, we were flying over Italy, and here was this Indian being treated by a Soviet doctor who was using a Tibetan balm, a medicine, to massage my back. So there you have it, 2 examples of a multinational crew and international cooperation. But then, on a serious note, these are serious concerns. One is about sustainable exploration, and the other, how do we make this whole endeavor going forward inclusive for the people back on Earth? And there are United Nations resolutions already in place, but how do we make them work? So if I'd be very happy to hear the opinion of our esteemed panelists. Dr. Alice.
Thank you, Commander Rakesh. Thank you so much. I wish I could use the phrase "when I was in orbit." I'm deeply jealous that I cannot use that phrase. But seriously, I think your points around the challenges and opportunities of international cooperation are very, very on point. But first, let's talk technology, and let's talk sustainable technology. I think what's really interesting is if you look back over the last 60 years, the way we access space has hardly changed at all, and yet we know we want to go further. And you're quite right, we are more aware of environmental impacts and more aware of the need to evolve our technologies. So perhaps I could turn to my panelists for some further thoughts on what you think the new technologies will be that will support our future space travel. Jim, I see you've come off mute, so I'm going to take that as an indication that you want to come in. Günther, thank you. I see you put up your hand, so I'll come to Jim first and then to Günther. Thank you.
Well, in the immediate future, the concept of what we call ion engines, the ability to have a fuel, ionize it, and then accelerate those ions out the back using the, for every reaction, there's an equal and opposite reaction, has proven to be quite successful for a series of not only Earth orbiting satellites, but for planetary satellites. We used ion engines on a mission called Dawn. This enabled us to get into orbit at a beautiful asteroid, the second largest asteroid called Vesta, and then come out of that orbit, fly halfway across the asteroid belt, and then end up orbiting another spectacular asteroid called Ceres, which was the largest asteroid, get into orbit. And that was so fascinating, we decided to stay there, even though it had the capability to break orbit and go off to another destination. We wanted to learn so much more about these two beautiful objects. So ion engines in the immediate future are extremely important to be able for us to get around in a way that we can.
So maybe, Alice, Jim has almost taken the word out of my mouth, because indeed, Bepi Colombo, for instance, is on its way to Mercury using electromobility, as we say. We are using ion thrusters, and this is clearly a very exciting way for the future. What I have written to an answer in one of the chats was that also, for instance, on the space station, we are burning metals and try to understand how metal fronts are burning. And actually, there are very powerful fuels that could be completely carbon-free, that could, in principle, be metal burning. They could replace some of our carbon economy here on Earth and on space. So there are quite exciting possibilities for the future.
Thank you, Jim. Thank you, Günther. Indeed, we're always very pleased to see when those technologies that are really pushed to their limits through our efforts on space exploration also find application back on Earth, and we know that very often happens too. Why don't we talk about international cooperation next? It's interesting, there's a number of different questions in the chat which somehow or other relate to the need for international cooperation. There's the observation that there's lots of new entries. I mean, it was fantastic to hear from our panel today firsthand about Mars Perseverance, about Tianwen. Of course, UAE have had a fantastic achievement with their HOPE mission recently as well. So we are seeing more and more international players, and with that there will be many, many opportunities, but there will also be some challenges if we're not careful to coordinate. There was a further question around the challenges of data exploitation. And I noticed in Professor Yidong's presentation, you talked often about international collaboration. You talked also about making data freely available to scientists to take forward in that cooperative, collaborative way our understanding that we gain from some of these space missions. So I wonder if I might turn to you first for your reflections on what are the important elements that are needed across international cooperation that we will need to, as a humanity, get the most from our space exploration efforts. Where do you see it working well? Where do you see that we need to take more efforts? And I am hoping...
Yidong, yeah, he's...
Yeah, in fact, in our mission, some other country scientists join us. For instance, some you see we have astronomy satellite swarm. The class participant the mission, and we had new satellite mission called EP Einstein probe. Also the class and the ESA and also the Germany scientists join us. For the future plan, we have also a foreign partner join us. I think that in the scientist level, there's some no difficulties, but the company level may be some problem. Especially, of course, United States have some concentration. So this is some other reason. But I think maybe, first of all, the scientist level should enhance the exchange and to found the common interest. Then to push the agencies level to push the cooperation. Of course, for a larger mission, something like the human lunar mission, maybe must negotiation between the government. This is some other reason. I think maybe we need more and more time to resolve some recent difficulty. I mean, is in the scientist level, we can do more. That's all. Thank you.
Thank you. I think they are incredibly important points, and I think very often we look to the science community to help bridge and form collaborations which otherwise are made more difficult. And I certainly note your observation that there may be more work ahead, particularly as we see the increased cadence of missions going back to the moon.
Well, while we're waiting for Alice to come back, let's stay on that theme, because international cooperation is so very important. I mean, I think the International Space Station as a joint capability of this world is just a tremendous example of that kind of cooperation. We have different cultures, different political systems, but learning to live and work together on space station is really so exhilarating for promoting cooperation between nations. Also in the chat, there was a number of people that mentioned about, well, how can other nations get involved? Every nation can get involved.
Let me add a little bit.
So much we need to do and wanted to work. Oh, please, Mikhail.
Professor Marov, please go ahead.
Thank you. My point is that international cooperation is extremely important. Well, it's even, addressing back to the history. It's just allowed us to weaken a little bit, at least, some tension between countries. And for example, Soyuz Apollo mission speaks in favor of such kind of allegation, okay? Also, just saying about the current time, we, as I said, in the very tough situation with our national space program, we were very much benefited to have an opportunity to install our instruments on board of NASA and ESA missions. In particular, we still very much happy having important results derived from Lunar Reconnaissance Orbiter, LRO, and also from Mars Odyssey. There are quite capable instruments developed by my good colleagues in Space Research Institute. There are some neutron monitoring of the surface of these bodies in order just to reveal the contents of hydrogen-bearing compounds. And the most, I would say, probable hydrogen-bearing compounds are just traces, at least traces of water. And such instruments return back already very important information. We also have instruments installed on Bepi Colombo, and it's also quite promising for taking data from this mission, specifically about the water abundance in the upper surface layer of Mercury? Well, certainly there are extremely important cooperative programs between different astronauts on board of the International Space Station. Unfortunately, this is not quite plain sailing, because such I mean at the level of scientists, very, I would say, even interesting proposal, very interesting projects, they are not very well supported by some leaders of the country because just of some not quite positive political motivations. And this is very unfortunate for straight and for cooperative programs. I very much hoping that the situation in space area will change in the positive way, and it will benefit in particular not only some scientific endeavors, but also in the relationship between countries. We very much happy, just to recall, also to have joined cooperative program with ESA right now, with Exomars spacecraft. And this is not just, some kind of airing efforts, but it's really implemented in the design and in the manufacturing of special segments of these vehicles. For example, Russia right now, in the second part of Exomars mission, responsible for this, basically landing of the whole scenario of landing on the Mars surface in order just to deploy the Mars rover and operate on the Mars surface. And we install very capable scientific instruments on the landing platform and partially on the Mars rover. So I very much hoping that the situation will be, improved, and as I said, will benefit to the all countries. We also, just also to mention again, we have also very good cooperative program right now with China, with the Chinese scientists. And this is not only limited by the Moon program, but also extended for some other ambitious programs. That's my point.
Alice, maybe just... May I just one sentence?
Go ahead.
Sorry, just to... So I think international collaboration is absolutely essential. It is much easier on a bilateral level, and typically where basically one partner is has the lead, and then another partner can join in, as we do, for instance, with NASA very efficiently. And also we are collaborating with China and with Russia on the Exomars. The big international collaborations, the multilateral collaborations, are much more complex, and I believe they really require political will, like the space station, for instance, or the lunar gateway. But I would like to go back to something that Mikhail has said. When we were young, we were in the middle of the Cold War, but still the two blocks were collaborating in space. I mean, I personally was in an institute which flew an instrument on the Russian space station, and we learned Russian cosmonauts' personal lives and so on. And you know, the Sting song, the Russians love their children too. I believe this feeling of a personal relationship has helped that the Cold War went without a shot. And I believe this is something for the future as well. It's absolutely essential to have peace on Earth, and we will be able to help that.
I appreciate that you mentioned about this the absolutely fantastic time when the astronauts from the different countries had a chance to fly on the Mir orbital station. You know, it was many countries involved in this process, but I completely agree that's much easier to implement some kind of the bilateral cooperation. But, well, we have very nice exemption, and such an exemption is International Space Station. Possibly it will be extended up to the moon and beyond.
I mean, this is really at the heart of the debate for me, and it is very inspiring to recall those occasions when the cooperation has really surpassed some of, if you like, the geopolitical differences that are happening on Earth. I was lucky enough myself to have a metallurgical experiment flown on Mir, so I have benefited firsthand. I think it's also worth reflecting on the developments that took place in the field of meteorology. Towards the end of the 70s and, the late 60s. I think that was a really tremendous accomplishment to have that partnership in place across the US, Russia, China, Europe. It's extraordinary, really, when you look back at that. So let's hope there is a hope there for international cooperation. I'm smiling as I look at Günther, because I know that day to day he struggles enough with that, with 22 countries in Europe arguing amongst themselves. And that's just in Europe.
Including yours.
I couldn't possibly comment. Oh, very, very good. Unfortunately, I think we've lost Dr. Jemison, because I was going to turn to her. We had some of the questions in the chat bar earlier around inclusivity, and I think Dr. Jemison made some really, really important points around inclusivity. In fact, speaks to this point around international cooperation. We will get the best out of our programs if we have the most diverse set of minds around the table. We are coming up to the end of our time. Unfortunately, as I keep getting kicked off the call, I lose the thread of the chat bar. So I'm desperately trying to recall, and I hope, as your moderator, I've adequately covered most of the questions that have been coming through the chat bar. Of course, thank you to our panelists, because I know that you have been intervening as the event has gone on to pick up individual questions. But I think as we come into the final moments, I should just, for my part, give a very sincere thanks to all the panelists for a very, very interesting discussion this evening. I'm delighted that we've had so many participants to this call too, notwithstanding the slight technical challenge that might have brought. So for my part, I think I would like now to hand over back to Joe.
And to Carol, I believe.
Perhaps I can jump in. I'm
Great.
always terribly fortunate as Master of St. Cross College to have the opportunity to thank participants in these extraordinary events. It is the home of the Centre for History and Philosophy of Physics at St. Cross here, and we do have the chance to hear the most amazing series of talks and debates amongst the world's greatest experts. I'm sure you would also be wanting me to thank the director of the centre, Dr. Joe Ashbourne, who brings these things together and comes to me with ideas, and I always think, good Lord, that's not going to be possible, and every time it happens. And this evening, I think we've had an extraordinarily broad international discussion. The talks and slides, even for someone like me who isn't a scientist, have just drawn us all in and raised so many questions and further things to go and explore. Alice did a fantastic job of bringing in the questions from the sidebar, and I was really grateful that people were answering questions as we went through. So many of those questions have just been answered as the talks were going through. That move from competition to collaboration and joint working internationally has come through very, very strongly this evening, along with the honesty of all of the participants who've talked about the challenges and when they had failures as well as successes. So I'm so grateful for the really exciting presentations that we've had. I'm also very conscious that it's all happened in my lifetime. We talked about 1957 as the beginning, and that was the beginning for me as well. And the excitement of what might happen in another lifetime is completely mind-blowing. So I would just like to thank everybody who's taken part today, the nearly 500 people who've been online and watching, and all of the panelists, the speakers, and Alice for bringing everything together for a really inspiring evening. And I, for one, have had all of that excitement of space travel and space exploration brought back in really stellar, multicolour excitement this evening. Thank you so much, everybody. And thank you for all of those who joined us tonight.
And thank you, organizers.
Yes, thank you very much. It was a great pleasure.